So one additional test that we're going to look at beyond the nth term test for divergence and the limit comparison test is this test called the direct comparison test. The beauty part about the direct comparison test is it follows really closely what we already know to be true from the limit comparison test. And we're directly comparing some known series, we're still going to call it B sub n, with the unknown series that they're giving us, and we're still going to call that A sub n. And for direct comparison, if A sub n is less than B sub n, and we know B sub n converges, then any series smaller than B sub n must also converge. And here is a graphic look at the same thing. So if we know the red series converges, any series smaller than it or less than it must also converge. And if the relationship is opposite, if B sub n is smaller than A sub n, and we know B sub n diverges, then any series larger than B sub n must also diverge. That follows directly from what we learned on the limit comparison test. So it looks and feels a whole lot like the limit comparison test, but this is a direct comparison. There will be no limit involved here. We're just going to do a direct comparison between the nth terms of A sub n and B sub n. And the direct comparison test can be used on series that are not strictly positive. We can use them on all types of series. So just as with the limit comparison test, where we run into trouble is if we find out that our unknown series is bigger than our known series and our known series converges, that's not useful. If A sub n is bigger than a convergent series, A sub n could converge or it could diverge. So the direct comparison test, just like the limit comparison test, it's important that you are using a good comparison that is useful. If the unknown series is smaller than a divergent known series, that's not helpful either. A sub n is smaller. It could converge. It could go ahead and diverge, just at a rate lower than that divergent series. So we have to pay attention to the stuff that we learned from the limit comparison test and bring it here to work with us with the direct comparison test. Now, when we have a series that looks like power terms, I'll just be really honest with you. If I had a series that looked like that, I wouldn't think of using the direct comparison test. That's screaming at me, use the limit comparison test. It's, I could put that inside of a limit. I can run as many iterations of L'Hopital's as I need to. It would be really easy to find a series to compare it to. So this just screams limit comparison test to me. But I want to prove to you that we can use the direct comparison test and get along just fine. Now, with the direct comparison test, the power in this lies in finding a B sub n, but now instead of being concerned about how A sub n acts for large n, now we're concerned about how we can come up with a B sub n that acts like it and that is either bigger if we have a divergent B sub n, or smaller if we have a convergent B sub n. So there's a lot more factors in play here. Not only do I need to come up with a B sub n that acts like it for large n, just like in our work with limit comparison, the minus 4 is of no consequence. N over 5n squared is acting like 1 over 5n. So for large n, I would want to compare A sub n with the harmonic series. And just like in limit comparison test, in direct comparison test, I still need to justify what's happening on B sub n that I'm comparing it to. All right? So the power here, and I'll bounce down here a little bit, is in the denominator. Look at your denominators. Because when we're comparing fractions, if we have this is greater than that, then when we put those things into a fraction, if this is a bigger output than this, if that's a bigger value, when I make them the denominator of a fraction, that reverses that relationship, right? So what I want to do here with the denominators of my fractions is I would like, since I'm comparing to a divergent, I would really like this relationship to go on. I want A sub n to be bigger than or equal to B sub n. That's the only comparison that's going to help me. So I need for the denominator in A sub n to be smaller than the denominator in B sub n. Well, I know that is absolutely a correct statement. If I take n, I don't care what value n is, small or large, and I square it and I multiply it by 5, when I subtract this 4 over here, that's definitely going to be less than 5n squared. And the power of that is, when I put those in the denominator of a fraction, I just reversed that relationship. Now, notice my numerator is not 1, it's n. Well, that's okay, because as long as I'm doing the same operation on both sides of my inequality, that's not going to affect what's happening. So, if I say that B sub n is 1 over 5n, which is what this is acting like, and I know that B sub n diverges, then I would say that my original series from n equal 1 to infinity of n over 5n squared minus 4 diverges by the direct comparison test. This one is not, I don't think, as intuitive or as straightforward as the limit comparison test, but there are some things that we would need to do. The first thing you need to do is determine what you think A sub n does. For large n, it looks harmonic to me. So I want to find a B sub n that I can prove that it is bigger than. That starts in the denominator. If I can prove the denominator of the unknown is smaller than the denominator of my known series that I'm going to use for direct comparison, then I need to show the AP reader the direct comparison between the unknown and the known. Here's the unknown they gave me, A sub n. Here's the known that I chose, B sub n. It is harmonic, and I do need to state that this is what I'm using, but I can write it in any form that I need to, and that's the form I need to write that harmonic in. And by direct comparison, since the unknown is greater than the harmonic series, then the unknown, A sub n, must also diverge by the direct comparison test. So you say, well, if we can use the limit comparison test, that makes more sense. It's not so hard to find B sub n. We don't have to play around with how it looks. Why don't we just always use the limit comparison test? Well, because not every nth term is conducive to being put into the limit and taking into infinity. Because I don't know about you, but I don't know the derivative of n factorial. And everything that we did before, even though we didn't show every single solitary little step along the way with, whatever we were doing, even though we didn't show all those steps, if we had shown all those steps, by taking the derivative and applying L'Hopital's rule over and over and over, this is a mathematically sound result from good calculus. I don't know the derivative of 1 over n factorial or 1 over x factorial. The limit comparison test is not going to help me here. So there is a need and there is a use for the direct comparison test. You just have to make a good choice for B sub n. So for large N, what is 1 over n factorial acting like? Well, that's kind of hard to see sometimes. I don't know. N factorial is a pretty huge number. The larger n gets, which is where convergence and divergence happen, near infinity, the smaller and smaller and smaller these terms are going to get. 1 over huge is tiny. So I really don't know. One comparison with my denominators that I could make, though, that I'm really confident of, is it is a fact that I don't care what n is, but most especially when n is large, n factorial is bigger than n. So if I want to come up with a comparison, then that would be a true statement. But here's the problem. Do I want to compare to a divergent in the way where my unknown is smaller than a series that diverges? I really don't. That's not helpful, even though my algebra is spot on. This is a true statement. This is a true statement, but it is not helpful. So you have to take a minute and think about what's happening here inside your series for large input values. For large input values, those terms near infinity are getting super, super, super small. I mean, 6 factorial is 720. So by the 6th term in this series, we're adding 1 720th. And then it's 1 over 7 factorial, and 1 over 8 factorial, and 1 over 9 factorial. Those are the kinds of terms that we're adding here. So I really think, and I may be wrong, but I really think this thing converges. So I need to find a series to compare it to that I know for certain converges. Well, here's one. This is a pretty handy one. It's easy for me to show the AP reader that I know it converges. It's something where I can tell you absolutely, beyond a shadow of a doubt, that that is the relationship between n factorial and n squared. And if that's the case, this is the relationship between those two series. And the beauty part is that this unknown that I have chosen is a p-series, where p equals 2, which is greater than 1, which means this thing converges. And that's a good result for me. Because if I can prove that my series is smaller than a convergent, I can use that. So since this is the relationship between my unknown and my known, and I've clearly shown the AP reader that my known is a convergent series, then my original series, the original unknown that they asked me about, must also converge, and I can justify it by the direct comparison test. Now, it's not enough, I want to be clear, I know I'm about out of time, but it's not enough that I just show that. I have to show this as well. You have to prove to the AP reader that you know beyond a shadow of a doubt that is the relationship. And that is only going to be that relationship if this is the relationship in the denominators. So those two steps, absolutely important. This step would have to be shown. Then you actually answer the question. So there's the direct comparison test. We don't run the direct comparison test as often as we do the other test. It's kind of sort of the last resort, but it is something that works for us. So come to class next time and we'll do some practice problems.